Welcome back to the deep dive, where we cut through that informational fog and really deliver the concise, actionable knowledge that makes you, our listener, the expert in the room.
That's the goal.
So if you were with us for our first view into cloud operations, you've already built that foundation. You learned the basic vocabulary, the what and the where of logs and metrics.
Right. It was the 101 course.
Yeah.
You have, a fuzzy high-level map of the territory.
Mm-hmm.
That data needs to be collected, it needs to be monitored. But, modern cloud infrastructure it's just vast, it's distributed, and it's incredibly dynamic.
Right.
So to really master operations, we need to move beyond those, general concepts.
Exactly. Today is the second view. We're shifting gears from that basic conceptual understanding to the intermediate strategies and, the specific technologies you use when performance bottlenecks are hiding in microservices.
Which they always are.
When security is paramount and when you are dealing with millions of log entries an hour. Our mission today is laser-focused on the technical core of cloud operations and monitoring.
Yep.
We're talking about how to route data intelligently, set up alerts that actually mean something, and unlock the specialized investigative power of tracing and profiling.
We're moving into the intelligence domain. That's the key shift.
Correct.
It's no longer enough just to, collect data.
Right.
You need an architecture that ensures zero loss, instant reaction capability, and crucially, the ability to zoom in from a system-wide failure, way up high, all the way down to a single inefficient line of code.
From the macro to the micro.
Precisely. We're going to solidify these intermediate best practices and make sure that complex concepts like, say, log syncs and memory gauge types, they become intuitive tools in your operational arsenal.
Okay, let's unpack this source material, starting right at the beginning, but with a critical eye. Cloud logging. This is the digital flight recorder for every single action that happens in your environment. But we have to make sure we're setting up the recording mechanism correctly from the very start. When we talk about cloud-native operations, and specifically running containerized workloads on something like Google Kubernetes Engine or GKE, the rules just change fundamentally from the old server days.
Completely different ballgame.
In a traditional setup, you'd probably have your application writing log files to disk. But if you have production pods churning away today, what is the Google recommended, the truly cloud-native way for those applications to output their logs so the platform can reliably capture them?
The foundational answer, and the one that really adheres to the spirit of containerization, is to write logs to standard output and standard error.
So stdout and stderr.
Exactly. This is often labeled as the 12-factor app logging standard, but its application in the cloud is just. It's critical for efficient operations.
I know so many teams struggle with this transition. Why is writing to, say, varlogme-app.log inside a container? Why is that a bad idea? Even if it worked perfectly fine on a traditional VM, what operational headaches does that old approach introduce?
Well, the headaches are manifold, and they really boil down to efficiency, overhead, and reliability.
Okay.
First off, containers are ephemeral. That's the whole point.
They come and go.
They come and go. So if a container crashes or restarts or gets scaled down, any data written to its local file system, including a log file in varlog, it's usually just gone. You lose the entire context to the crash.
So the evidence disappears with the container.
The evidence is gone. Second, there's overhead. If you write to a file, you introduce this whole new layer of complexity because now you need a logging sidecar or, a custom agent inside the container.
Right.
Specifically tasked with watching that file, handling file rotation so the logs don't fill the disk, dealing with permissions, and then pushing the data out to your central collector. All of that adds CPU and memory overhead to every single pod you run.
So if the application just writes to stdout or stderr, what's the difference? Who's doing the heavy lifting then?
The container runtime itself, Docker, containered, whatever you're using, it captures those standard streams natively.
Okay, so it's built in.
It's totally built in. The primary logging agent that's already running at the node level on GKE, which is often Fluent or Fluent Bit, is configured out of the box to collect these streams automatically from the runtime.
So the application developer doesn't have to think about it.
They just print a line. That's it. The platform guarantees its capture, its routing, and its indexing and cloud logging. You simplify the application, you reduce overhead, and you increase reliability because you're letting the infrastructure automation manage log transport, which is, that's exactly what we want.
That's the classic case of leveraging the platform's native capabilities. Okay, now that the logs are reliably collected in cloud logging, we need to talk about their life cycle and where they go next. This is where the system stops being just a simple collector and starts acting like a highly efficient data router. Our first routing challenge is security-driven. We have a mandate to stream all Google Cloud audit logs, which can be extremely high volume, to a third-party security information and event management system, a SIEM, like Splunk.
A very common requirement.
And this is critical for real-time threat detection and forensic analysis. So what is the standard, reliable, operational pattern for streaming this high-volume security fire hose out of the cloud and into an external critical system?
The design here has to prioritize durability and real-time delivery above everything else. The standard resilient pattern is to create a log sync in cloud logging with a pub sub topic as the destination.
When we talk about intermediate architecture, understanding the why of that middle piece is, I think, essential. Why can't the log sync just send the data directly to the external SIEM, via an API endpoint? What failure scenario are we explicitly trying to prevent by putting PubSub in the middle?
We are preventing a really crucial failure scenario known as back pressure and data loss.
Back pressure, okay.
Log syncs are designed to capture data incredibly fast, but external SIEMs have a finite ingestion capacity. So what happens if that SIEM server goes down for maintenance or simply gets overwhelmed during a peak usage hour?
Right.
If the log sync tried to stream directly, it would eventually fail to connect or, it'd get throttled. And that could lead to the loss of critical audit logs, which is a compliance and security nightmare.
So PubSub is our resilience layer. It's a buffer.
Exactly. PubSub acts as a highly durable buffer, or you can think of it as a highly scalable message queue. The log sync publishes data instantly to the PubSub topic, which handles throughput spikes with ease.
It just absorbs the burst.
It absorbs it. The audit logs are guaranteed to remain in that PubSub queue until the SIEM's ingestion mechanism successfully acknowledges and consumes them. This decoupling ensures that cloud logging can focus on capturing data without worrying about the external system's health.
And the SIEM gets the data in real time.
The SIEM gets the data in real time, fulfilling the security requirement without ever compromising durability.
That concept of instant reliable delivery, that leads us to the next operational requirement: real-time anomaly response.
Active remediation.
Right. So if the security team detects an unwanted change, say a critical firewall rule being opened or credentials being accessed abnormally, something truly urgent that requires immediate action, we need automation to roll it back or disable the user. We can't wait for a human to read an alert.
This moves us from passive monitoring to active event-driven remediation. The solution has to be fast, it has to be serverless, and it must be triggered instantly upon log entry creation. The best practice here is to export logs to a PubSub topic and trigger a cloud function with the relevant log events.
Okay, walk us through that sequence. How much time are we actually talking about between the event happening and the remediation code running? Are we talking minutes? Seconds?
We are talking about near instantaneous sub-second execution. The mechanism is really powerful.
Okay.
First, the critical event, like that firewall change API call, gets written as a log entry.
Right.
The log sync, which is filtered specifically for that one event type, immediately routes it to a dedicated PubSub topic.
So it's not sending everything, just the interesting stuff.
Just the critical alert. That PubSub message then instantly triggers a pre-deployed serverless cloud function. And then fourth, the function executes the necessary remediation code, maybe calling the firewall API to revert the change, or sending a command to revoke the user's token.
And you contrast this with the slower alternatives. What would those be?
Well, you could schedule a server to pull logs every minute, but that means you have a minute of exposure.
Which for a security breach is an eternity.
An eternity. Or you could wait for a BigQuery analysis, which introduces minutes, maybe tens of minutes of delay. For security incidents, speed is the definitive operational metric, and that PubSub to cloud function pipeline. It guarantees that immediacy without the complexity of managing an always-on remediation server.
Now we address the long game. Retention and compliance. Our organization operates in a regulated industry and must retain all application metrics and raw logs for 5 years.
5 years is a long time.
It is. For potential legal discovery or complex forensic analysis, cloud logging's default retention is much, much shorter. So where do we archive this massive volume of historical data cost-effectively and reliably?
When the requirement is long-term, high-durability storage, cost has to be the primary driver. The solution is a strategic export. Configure monitoring for all projects and export the data to Google Cloud Storage.
Okay, I have to challenge this a little bit because BigQuery is Google's massive data warehouse designed for analytics. Why is cloud storage, GCS, which is essentially object storage, superior for this 5-year retention mandate? Isn't the whole point of storing data to be able to analyze it later?
That is an excellent intermediate level distinction, and it comes down to the access pattern and the cost structure.
Okay.
BigQuery is optimized for active analysis complex, rapid SQL queries across petabytes of, let's call it, warm or hot data. BigQuery is incredibly fast, but it carries a higher storage cost.
Right.
When you have 5 years of raw, high-volume log data, you know you will rarely, if ever, access most of it. It's dormant data required purely for compliance.
So it's cold storage. And GCS addresses that dormancy perfectly.
Absolutely. GCS offers various storage classes, nearline, coldline, and archive, which are exponentially cheaper than BigQuery storage. They're designed specifically for data with minimal access frequency.
But it's still durable.
Oh, incredibly. GCS provides 99.999999999% durability. If we need to analyze that data 5 years from now, we can just batch import the relevant GCS files into BigQuery at that time for that specific query, rather than paying BigQuery's high-performance storage costs for 5 straight years.
So you pay for the analysis when you need it, not for the storage forever.
Exactly. It's the compliant and, frankly, the fiscally responsible archival solution.
That clears up the archival choice. Now let's address organizational scale. We manage a massive organization with dozens of projects grouped into a single production folder. We need to ensure that every single log from existing production projects, and critically, logs from any new project created next year inside that folder, are automatically captured and exported to our SIEM. How do we future-proof this logging governance?
This is a classic governance challenge that absolutely demands a policy-based solution over any kind of manual configuration.
Because manual will always fail at scale.
It's guaranteed to fail. You'll miss one. If you try to configure syncs project by project, you create a guaranteed operational gap. The strategy is to create an aggregated export on the production folder.
What's the mechanism that makes this folder-level configuration so scalable and robust? What's happening under the hood?
By creating the log sync at the folder level, you are defining a rule higher up the resource hierarchy. Cloud Logging's aggregation capability ensures that this rule cascades down to all resources beneath it.
So it inherits the policy.
It inherits it automatically. If an engineer spins up a new project named Project 200 inside the production folder, that project automatically gets the aggregated export policy. The operations team never has to intervene, they never have to remember a checklist item, and compliance is guaranteed from the moment the project is launched.
It's policy as code, basically.
It's policy as code for your logs. This level of automation prevents those scaling gaps that just cripple large organizations relying on manual steps.
Let's dive into a truly advanced security requirement, the kind that moves operations into, high-trust security engineering. We need to verify the authenticity of our logs.
Non-repudiation.
Exactly. If our goal is to maintain absolute trust in the application's audit trail for compliance, non-repudiation, or security forensics, how do we ensure that a log entry, once written, has not been modified by an attacker or even a rogue insider?
So, limiting access with identity and access management, IAM, that's foundational.
Right.
But it's insufficient because a sufficiently privileged attacker could still manipulate the record.
Right.
The solution requires cryptographic proof. Digitally sign each timestamp and log entry and store the signature.
Wait, digitally signing every single log entry sounds computationally heavy. If our application is processing thousands of transactions per second on the critical path, does this process of hashing and signing introduce noticeable performance overhead or latency? And how do we even manage the cryptographic keys required?
That is a critical operational challenge, and it's why this solution is reserved for mission-critical, high-trust audit trails. Yes, cryptographic signing is computationally expensive.
Right.
But the key is where that signing happens. Ideally, the application generates a cryptographic hash of the log entry before it even sends it to stdout.
Okay, so it happens inside the application code.
Inside the code. That hash, along with the log entry and timestamp, is then signed using a non-repudiable private key, which is often protected by a managed key management service or a hardware security module.
So the performance trade-off is unavoidable, but it's acceptable in these high-stakes scenarios.
It is, because the alternative is a complete lack of trust in the system's history. The value of this signature is non-repudiation. If someone later alters even a single character in the log entry or the timestamp, the stored digital signature will fail validation.
So you have mathematical proof of tampering.
You have cryptographic proof. This is a much stronger guarantee than mere database access control. For financial systems, healthcare records, or critical security platforms, the minor performance overhead is just the cost of regulatory compliance and absolute security assurance.
This shifts logging from merely recording data to actively guaranteeing the integrity of history. That's a huge leap in operational responsibility.
It is.
We've established how to ingest logs natively, route them intelligently for real-time security, archive them cost-effectively, and verify their authenticity. Now let's pivot hard from passive data capture to active operational intelligence. Cloud monitoring.
Right. Monitoring is the intelligence layer. Logs tell us what happened. Monitoring tells us what is happening now, how frequently it's happening, and crucially, whether we are about to violate a service level objective. It drives automation and informs human intervention.
Let's start with the operational baseline. We manage a fleet of compute engine instances in a managed instance group. We need a fundamental alert. If the fleet's average CPU utilization exceeds 80% for more than 5 minutes, we need an immediate email notification. What is the tool we use, and what's the reasoning behind those specific numerical parameters?
The tool is the core of the system, a cloud monitoring alerting policy. And the reasoning behind the numbers, 80% and 5 minutes, is really the difference between genuine operational load and just noise.
Okay, unpack those parameters for us. Why 80%? Why not 95%? And why the 5-minute duration?
So the alerting policy requires the metric, the condition, and the duration. Setting the threshold at 80% is strategic. It's high enough to signal a significant and sustained workload, indicating the instance group is close to saturation, but it leaves 20% headroom.
And that headroom is vital.
It's vital. We set the alert at 95%. We might only find out when the system is already experiencing user-facing latency and errors. We're being reactive at that point. 80% lets us be proactive.
And the duration is our noise filter.
Exactly. The 5-minute duration is the filter against alert fatigue. Most modern applications experience brief, natural spikes. Maybe a database index is rebuilt, or a large batch job kicks off for 45 seconds.
Right, you don't want an alert for that.
You don't. Alerting on every one of those quick spikes means the operations team gets dozens of notifications that don't require action. By requiring the condition, the 80% CPU, to be sustained for 5 consecutive minutes, we filter out that transient noise and ensure we are only alerted to a genuine, persistent increase in workload.
Something that probably requires the autoscaler to kick in.
Right, or manual intervention to investigate. It ensures our alerts are high-fidelity signals, not just data noise.
Moving to integration, many listeners operate in environments that use established open-source tools. For instance, our employer uses Prometheus, known for its powerful PromQL query language, but they are tired of managing the underlying infrastructure.
The care and feeding of Prometheus servers.
Yes, the scaling, the storage, the sharding. They want the familiarity of their existing tooling combined with the scale and management relief of the cloud.
This is a classic modernization use case. The solution is to use the Google Cloud Managed Service for Prometheus.
What's the primary operational advantage that this managed service provides, especially compared to just, running Prometheus on a VM?
The primary advantage is operational relief and cloud-native scaling for storage. When you self-host Prometheus, you are constantly fighting data retention limits, storage compaction failures, and the enormous complexity of sharding your metrics data as your environment grows.
It's a full-time job.
It's a full-time job for a team. The managed service handles all of that seamlessly. The critical part, however, is that it supports Prometheus query language, PromQL, natively.
And that's huge for the teams already using it.
It's huge. For an operations team, this means they can continue to use their highly optimized custom alert definitions and Grafana dashboards that rely on PromQL. They don't have to rewrite thousands of lines of monitoring code or undergo a massive retraining effort.
So they just change the endpoint.
They just point their existing Prometheus agents, their exporters, at the managed collection endpoint, and the cloud handles the enormous, messy backend. It gives them cloud scalability while preserving their investment in established tooling and expertise.
Okay, here's where we hit the classic intermediate-level monitoring trap that trips up even experienced engineers. It requires a deep understanding of how Linux handles resources.
Yes, this one is tricky.
We have an application running on Compute Engine that is supposed to auto-scale based on memory usage, but it's failing to scale correctly under peak load. The monitoring is set up using the standard agent metric, agent.googleepis.com/memory%, and the filter is set for metric.label.state used. The target is 80%. When we check the instances during high load, they seem busy, but they aren't scaling. What is the fundamental conceptual error here, and how do we fix it?
This failure mode is so common because it relies on a a misunderstanding of the Linux kernel's memory management philosophy. The error is the simplistic reliance on metric.label.state used.
Tell us why that filter lies to the autoscaler. What's actually happening?
In Linux, memory labeled as used is highly misleading. Linux aggressively uses all available memory for file system caching and buffers. This is memory the kernel thinks is being used productively to speed up disk access.
So it's a performance optimization?
It is. But crucially, memory dedicated to buffering and caching is reclaimable. If your application suddenly needs 4 gigabit more memory, the kernel will instantly free up those buffered blocks without complaint.
So it's used, but it's not really in use by the application. It's available.
It's available on demand. So if your auto-scaling policy only looks at that simple use metric, that number often includes massive amounts of this reclaimable cache memory. The resulting percent used metric is artificially high, but the system is not actually under memory pressure.
I see. So the system might report 75% used, but 30% of that is just cache that can be dumped instantly.
Exactly. The autoscaler sees 75% and thinks everything is fine, while the application's true. Non-reclaimable memory usage might be creeping up, eventually hitting a wall and crashing.
So the key operational insight is that for effective autoscaling, we must measure the non-reclaimable memory pressure, not the total OS memory footprint. How do we structure the metric to achieve this accuracy?
We need to define a custom metric or a derived metric that effectively calculates the true available memory. This means we must filter for the states that are genuinely available or, subtract the reclaimable states from the total used pool.
Okay.
The technical fix in the monitoring filter should aim to exclude the buffered and cached states. You would define the memory available as the sum of metric.label.state equals free plus metric.label.state equals cached plus metric.label.state equals buffered.
So you add up everything that's actually available.
Right. And then you set the auto-scaling target based on the percentage of memory not included in that calculation. While the specific solution in the source material lists all 4 states used, buffered, cached, the slab to highlight that the labels exist, the operational reality for auto-scaling requires you to use these labels to calculate the actual depletion.
The lesson here is profound. An intermediate operator must understand not just which metric to use, but how the operating system calculates that metric, especially when it is used to drive automation like autoscaling.
Absolutely.
Failure to understand those internal states leads to scaling failures, overscaling, or just unnecessary cost.
Absolutely. Relying on default metrics without understanding their underlying system context is the fastest way to operational disaster. We need precision in our metrics to drive intelligent automation.
We've established how to collect data intelligently and how to set smart alerts based on aggregate metrics. But when an alert fires, say, request latency is spiking, the monitoring dashboard only tells us that the problem exists. We need tools to find the invisible culprit deep inside the application. This section is all about the 2 specialized microscopes for deep diagnosis, Cloud Trace and Cloud Profiler.
These 2 tools are, I would argue, non-negotiable for modern distributed systems. And they answer very different questions. Trace answers, where did the time go in the network and across microservices? Profiler answers, what specific code executed slowly inside a single application instance?
Let's start with the classic microservices pain point, latency. A small subset of API requests are suddenly taking 5 to 7 seconds, while the average is, say, 50 milliseconds. We know the request chain is long authentication, billing, inventory, notifications, and we need to identify which specific service is the bottleneck. General monitoring just gives us the high average.
If the latency is systemic and distributed, you need Cloud Trace. The solution is to instrument your application with Stackdriver Trace in order to break down the request latencies at each microservice.
Use that analogy again, but let's deepen it. If the request is a package, Trace is the GPS and the stopwatch. How does that translate into the actual data structure we see?
The data structure is called a trace, and it's composed of spans. Think of a span as a single time step in the journey. When the user clicks Submit, the first service, say the API gateway, starts the trace. When it calls the authentication service, that starts a new span that is a child of the original trace. The authentication service then calls the billing service. That's another child span.
So it's a hierarchy of calls.
It's a hierarchy. Trace instruments your application code to automatically send these start and stop times to the collector. The resulting visualization is a timeline graph, a waterfall chart. If the total request took 5 seconds, the graph might show a 5-second bar, but immediately beneath it, you see the individual spans.
And one of those will be really long.
Exactly. If the span for the billing service is 4.8 seconds long, you have instantly pinpointed the bottleneck. Trace is critical because it provides the context across network boundaries, something raw logs or simple metrics just cannot do. It moves you past guessing and straight to the failing service.
And the key point is the difference from general monitoring. Monitoring said latency is high. Trace says latency is high because the billing service API call took 4.8 seconds. That is an entirely different level of actionable insight.
It's the difference between knowing you're sick and knowing which organ is failing.
Now let's take the next logical step. Trace told us the problem is the billing service, taking 4.8 seconds. But now we need to know why that service is slow internally. The specific scenario is tricky. A Java application in production is chewing up excessive CPU, hiking up our cloud costs, but when the developers try to reproduce the issue in staging, the load isn't high enough, and the issue just vanishes. We need to analyze the production code's performance characteristics live without crashing it.
This is where you deploy the other specialized tool, Cloud Profiler.
Why is Profiler the only acceptable tool here? If a developer wants to find an inefficient loop, their natural instinct is to attach a debugger. What is the operational risk of using a traditional debugger on live production code?
The operational risk is catastrophic downtime. A traditional debugger is highly intrusive. It stops the thread or the entire application to let the developer inspect variables and step through code.
It freezes the application.
It freezes it. That interruption instantly breaks the user experience, leads to timeouts, and violates our service agreements. Profiler is fundamentally different because it is designed to analyze code performance on live production instances with minimal performance overhead, often less than 1 or 2%.
How does Profiler achieve that non-intrusive analysis? What's the trick?
It uses statistical sampling. Cloud Profiler is a lightweight agent that runs in the background. It takes rapid, random snapshots of the application's call stack, often hundreds or thousands of times per second. It's essentially asking the CPU, what function are you running right now, over and over again.
Okay.
Since the snapshots are random and frequent, the law of statistics applies. If a particular function, say validate massive invoice, appears in 90% of those random snapshots over a minute, Profiler can confidently report that 90% of your application's CPU time is being spent inside that specific function or the code it calls.
And what does the engineer see as the output? What's the final result?
They see visual aggregate data, usually in the form of a flame graph or a CPU heat map. This visualization instantly shows the hotspots, the widest, tallest segments of the graph that correspond to the functions consuming the most CPU time.
So it's immediately obvious where the problem is.
Immediately. This is invaluable because performance problems, especially in Java or Go, often manifest only under true production load, making the non-intrusive nature of the profiler the key differentiator for solving cost and performance issues.
So that distinction trace for distributed latency, Profiler for internal code efficiency, that is absolutely essential for any intermediate cloud practitioner to master.
Yes. Now we shift our focus from individual tools to organizational strategy. The best tools in the world are useless without robust processes and sound architectural consultation. This section addresses how we apply operational knowledge to design, disaster recovery, and team collaboration.
Disaster recovery. DR is often considered the ultimate operational challenge. We have a mission-critical application and need to develop robust procedures to test its disaster plan using native GCP capabilities. We need the recovery process to be repeatable, rapid, and verifiable. What combination of tools provides the necessary rigor for serious DR testing?
A true DR solution must mandate both automation and observability. You can't have one without the other. The correct, non-negotiable approach is to use Deployment Manager or a similar infrastructure as code tool like Terraform to automate service provisioning, and use Stackdriver, now cloud monitoring and logging, to monitor and debug your tests.
Let's elaborate on the role of infrastructure as code, or IAC here. Why is reliance on IAC paramount for a good DR plan?
Reliance on IAC is crucial because it eliminates human error and guarantees repeatability. If your DR procedure is a 50-step wiki page that requires clicking around the console, it will fail under stress, period.
Someone will miss a step.
Someone will always miss a step. IAC tools like Deployment Manager allow us to define the entire recovery environment network, instances, databases, load balancers in declarative configuration files. This means the environment can be reliably stood up with a single command, and just as importantly, reliably torn down when the test is complete.
And it's version controlled.
It's version controlled, meaning you know exactly which infrastructure configuration you tested 6 months ago. There's no guesswork.
And how does the monitoring and logging side of things turn that provisioning exercise into a genuine, verifiable test?
Automation provisions the infrastructure, but monitoring and logging provide the proof of success or failure. We don't just need to confirm the server started, we need to verify that we met our operational objectives.
The RTO and RPO.
Exactly. Monitoring is used to confirm that the recovery time objective, the RTO, how fast we got the system back, was met by tracking the time to baseline metrics like CPU and request latency. Logging is used to debug the application startup process and confirm no critical errors occurred during the database failover or service registration.
So without that integrated observability, you're just running scripts blindly.
You are. Stackdriver provides the verifiable, auditable data necessary to sign off on a successful DR test.
The operations team often sits at this critical intersection between business needs and technical feasibility, acting as a consultant to the development teams.
It's a crucial role.
Let's look at two scenarios where operational knowledge must guide design. First, a development team comes to us and says their existing older logging tool is inadequate for a new product. It can't handle the scale, the querying is too slow, they want a better tool. Before upgrading or forcing a new solution, what is the critical first step the operations manager must take?
The critical step is one of management and definition. Help them define their requirements and assess viable logging tools.
Why not just immediately recommend the native cloud logging solution? I mean, we just spent 10 minutes talking about how great it is.
Because a tool is simply a technology stack. Operational excellence requires us to match the right tool to the defined constraints. We need to quantify the problems their current tool has and set the benchmarks for the new solution.
So what kind of questions should we be asking?
Defining requirements means asking 1. Volume and scale. How many terabytes of logs will this new product generate daily? 2. Latency tolerance. Does the data need to be ingested in real time for security, or is delayed batch processing acceptable for daily analysis? 3. Retention. What's the legal retention period, because that impacts cost? And 4. Query complexity. Do they need simple text search or complex correlated SQL-like querying across traces and metrics?
And until you have those answers, you can't recommend a solution.
Until we have concrete numbers defining those constraints, we risk choosing a solution that is either vastly over-engineered and expensive or insufficient for their actual need, which leads to the same problem 6 months down the line. Defining requirements is the essential prerequisite to selecting the appropriate tooling.
That's the classic consultative approach. Understand the problem before prescribing the medicine. Okay, for our final, highly technical operational scenario, this one involving network design. A software engineer designs a new application using WebSockets, which rely on persistent, long-lived connections and critically non-distributed HTTP sessions.
That combination, WebSockets and non-distributed sessions, is an operational red flag that demands immediate attention.
Tell us why that design choice creates such a severe conflict with standard cloud operational practices and what the operations team must do.
The operational responsibility is to immediately intervene, meet with the cloud operations team and the engineer to discuss load balancer options. The conflict arises because most cloud environments use load balancing to distribute traffic evenly across multiple back-end servers to maximize resource utilization and ensure high availability.
Which is what you want.
It's what you want. But if the sessions are non-distributed, it means the state data like login info or shopping cart contents is stored locally on the specific application server that first handled the user's request. So if the load balancer sends the user's next request to a different server, that server won't have the session data, leading to an immediate application-breaking error. The user is logged out, their cart is empty.
So the standard load balancer, which prioritizes even distribution, is actively antagonistic to this application design. What operational solution can temporarily bridge this gap, and what are the risks?
The temporary technical solution is configuring the load balancer for session affinity, or sticky sessions, which ensures a user's subsequent requests are always routed back to the specific server that initiated their session.
But you're saying that's a compromise.
It's a huge operational compromise, not a best practice. It introduces significant risks. First, hotspots. If one user is very active, that single server can become a hotspot, buckling under load while other servers sit idle, which defeats the purpose of load balancing.
And second, failure.
Failure. If that single server fails, all the sessions attached to it are instantly lost, leading to a large number of frustrated users and a major session outage. It's a significant single point of failure.
So what's the long-term fix?
The operations team must communicate these constraints and risks to the engineer. The ideal long-term solution, which we would recommend, is moving to a distributed session management service, like a managed Redis cluster. That decouples the session state from the compute instance, allowing the load balancer to distribute traffic freely without session affinity, which dramatically improves resilience and scalability.
But the immediate step is that consultation.
The immediate step is consulting on the load balancer configuration required by the existing application design.
That scenario perfectly encapsulates how operational maturity means influencing architecture, not just managing infrastructure. This has been an incredibly deep exploration into that intermediate layer of cloud operations and monitoring. We began by focusing on logging integrity, ensuring foundational data is captured natively via stdout and stderr, strategically routed using log syncs and pub/sub for real-time security, and archived cost-effectively in cloud storage for 5-year compliance.
We then moved into the intelligence layer of cloud monitoring, where precision is paramount. We discussed how to define high-fidelity alerting policies and critically expose that common trap of using default OS memory metrics, emphasizing that successful autoscaling requires understanding and filtering for non-reclaimable memory pressure.
And finally, we differentiated the two powerful investigative tools: CloudTrace, our detective for finding distributed latency across microservices, and Cloud Profiler, the surgical code microscope for identifying high CPU consumption in live production code with minimal overhead. The operational mastery comes from knowing which specialized tool to apply to which specific problem.
The core takeaway is that moving to the intermediate level of cloud operations means leveraging platform automation, not just to keep the lights on, but to create intelligent, resilient, and verifiable systems. Operational intelligence minimizes noise, it maximizes efficiency, and it reduces manual intervention.
And before we sign off, let's just revisit that idea of logging authenticity, the need to digitally sign every log entry. That requirement raises a fascinating operational challenge that is becoming increasingly relevant. If every piece of application data and every log record must be cryptographically verifiable to guarantee its integrity, this forces security and non-repudiation into the fundamental design philosophy of the application from day one. It means moving beyond logging as just a troubleshooting mechanism and toward logging as an immutable, auditable system of record.
Designing systems where integrity is guaranteed by architecture rather than just by policy, that really is the next frontier of secure, observable applications, and it requires this kind of integrated thinking we explored today.
Absolutely. Thank you for diving deep with us. We'll catch you next time.